Hello, welcome to the video. And in this video, we are shifting gears, and now, in from this video onwards, we are talking about the CMOS processes and implementation in CMOS processes. So far now, as of now, we have covered the concepts of negative feedback loop, op-amps in negative feedback loop, their stability, and we also looked at the making of op-amps at level of current controlled voltage sources and voltage sources. Now let's deepen the process, and now we will realize the concepts and their implementation in CMOS processes. So let's talk about the components available in CMOS processes. So basically, in CMOS process, we have a P substrate, and if we want to make a MOS transistor, NPN transistor, so we dope it by N plus, and we have our polysilicon layer, and this is how our NMOS is made. And simply saying, if you want to make a PMOS, then we dig a N well and put P minuses, and again, this is a polysilicon layer, and which gives us the PMOS transistor. So as an IC designer, we have to play in two dimensions, and we cannot play in these dimensions because these are already fixed by the process team. All we have is we can play from the top view, and the two dimensions we get from the top. What do I mean by that? Let's discuss it further. So we have resistors, and resistor of are made of polysilicon layer, and which is used for MOS gates, and which are usually of very high conductivity. And if we are using a metal layers for very low value resistors, then it's possible to make high conductive resistors. So like, it might contradict the sentence, but like, if there are metal, and we can use those metal layers to make a very low value of resistors. So again, we have capacitors. So we use metal plates which are separated by dielectrics, and we have inductors. Because of limitations on size, the value of inductance is very small and very limited when it comes to a CMOS process. And we can make an inductor. Usually it's not uh, makeable, but we can make an inductor by using planar spirals of metal, something which looks like this, but again, it's not advised. And the use of inductor is prohibited, not prohibited, but they don't like to use inductors, so due to its bulky nature. And now let's look at the resistors in CMOS process. So as we discussed, we have a P substrate, and we have different metal layers. And in these metal layers, let's say from point 1 to point 2, there is a polysilicon layer, and whose thickness, let's say it is T. And so now the P substrate and the thickness of the metal, these all things are already designed by the process team. And what we have, as we discussed over here, we have the freedom to work in the top view. So if we take a top view of this register, so we have register from point 1 to point 2, which is our polysilicon layer, and it has its width and it has its length. So we only have the freedom over width and the length, and we don't have the control over the thickness as well as the resistivity of the material. And now the resistance between the 2 points 1 and 2 um, is given by R12 equals to the resistivity multiplied by the length divided by the cross-sectional area, which is basically omega times the thickness. So now over here, the resistivity and the thickness is already decided by the process team. So this is a constant value, and which is fixed already, and we are provided with the sheet resistance. So basically, sheet resistance is this value, which is rho by T, resistivity by thickness, and it is denoted by RSH, or R sheet, R square. And basically then R resistance becomes sheet resistance multiplied by length divided by width. So usually sheet resistance is given as RSH, which is let's say for an example, we have a sheet resistance of 100 ohms per square uh, area, so per square micron, let's say. So we have to make let's say we have to make a resistor of 1 kilo ohm. So we can say that we are given of resistance sheet resistance of 1 square, and for that to make we consider width 1 and length 10 times 1. So we are using 10 squares, and thus we can make a resistor of 1k using the L by W ratio as 10. So when we multiply it with sheet resistance, we get it as 1k. So this is how we make a resistor. And now the question is, how do we decide the value of omega and L? Sorry, not omega. How do we decide the value of width and the length? So in general, there is a limit on how small you can make any dimension, which is specified in the process itself. And let's say we hear of 90 nanometer CMOS technology. So basically, it means that the minimum gate length is 90 nanometer, or it also can mean that the minimum spacing between the metal layers is 90 nanometer. So that implies a 90 nanometer CMOS technology. So one of the features of the IC process is that all the components are manufactured simultaneously. That means all resistors are doped simultaneously, and which means that if we make two identical resistors, they will have the same value. So let's discuss about it. So let's say we have two resistors whose width and length are same, so we can call them identical, and they will have same value. So actually it's quite difficult to make exactly accurate value of the component. For example, when we manufacture the thickness or the resistivity of polysilicon layer, it can be different from what we expect. So also the semiconductor doping, which influences the resistivity, cannot be accurately fixed, and which means that the resistivity and the thickness can vary, and thus our sheet resistance can vary. And actually our sheet resistance varies a little bit, and typically when we have sheet resistance of, let's say, 100 ohm per square, so it really means that it probably is between 80 to 120 ohm per square microns, let's say. So but what important is identical component will have same value. So let's say both have the sheet resistance of 80 ohm per square, so its length is 10. So basically it gives us the if its length is 10 and it has sheet resistance of 80, both of them, then we will get 800 ohms, and the value of both resistors is same. And even though both will be of 800 ohms, although the absolute values will not be accurately fixed, and which can be varied through the due to the sheet resistance. So they two are identical, but their absolute value might differ a little while making them. So even though in identical components, doping will leave some errors and the edges may have some errors. So let's say we make thousands of the resistors of 800 ohms. So not just two, we make a batch of 1000 resistors of 800 ohms. So they will have average value of 800 ohm, but the exact value of each and every resistor will differ a little bit, and that is due to the doping, which will leave some errors. And let's say the edges might have some errors, like the edges may not be proper. So let's say we like because we rely on matching of these resistors. Example, non-inverting op-amp, uh, basically when we design our process, like we design our circuits, so we rely on matching of the resistors. And example of it is a non-inverting op-amp, where the gain depends on the ratio of the resistors. The ratio is inaccurate. As we discussed, there might be some errors while making the resistors. So if the ratio is inaccurate, the gain will be inaccurate, and there is a certain inaccuracy we can tolerate, but not more than that. So resistors must not be inaccurate by more than some amount. So let's say we have a distribution of all those 1,000 resistors, and whose value is, we are supposed that it's 800. So the average value of all will be 800, but the Gaussian graph gives us some deviation, which is sigma. And let's say this value is 800 minus sigma, and this value is 800 plus sigma. So from the Gaussian graph, we can say that 99.9% samples from 1,000 register lot, 99.9% samples will be within the range of 800 ohm plus minus 3 sigma. So basically, we need to know the value of sigma, and while knowing the value of sigma, let our R naught be 800 ohm, which is our nominal value of average of large number of resistors. So let's take delta R as the variation from the nominal value, and we have our delta R by R naught, and this is specified at some percentage. So let's see, and we have, let's say we are making two resistors. So delta R is the difference in the values of two resistors, let's say R1 and R2. So R sigma times delta R by R naught is equals to AR divided by root of omega L. And AR is something which is some value, some percentage in micron. So for example, we have AR of 2% micron. So we have a resistor whose width is 1 micrometer and whose length is 25 micrometer. So we can say that our sigma times delta R by R naught is basically this value, and this is our standard deviation, and which is 0.4%. So if the sheet resistance is taken as 100 ohm per square, then this will have a nominal value of 25 times 100, which is 2.5 kilo ohm. And if we make these resistors on a chip, we expect that there will be a variation of delta R, and the standard deviation of that variation will be 0.4%. So to make it more accurate, we have to increase L and omega, not omega, width. So to make it more accurate, we have to increase the length and the width of the resistors, as standard deviation is inversely proportional to the root of the area, which is length into width. So let's take, we have a resistor and it has some variation delta R, and its nominal value is R naught. So basically its value is R naught plus delta R, and thus our standard deviation is sigma 1. So now from let's see, we take four such resistors and connect them, two in series, and these two in parallel. So each of them will have their own different variation, and which is random variation due to their own design or own dimensions. So let's say that resistance 1 provides R naught plus delta R1. Similarly, second provides R naught plus delta R2. Third one provides R naught plus delta R3, and fourth one R naught plus delta R4. So these are the resistances provided by these resistors, and each resistor will have random variation because each variation comes from individual distribution of dopants and etc. So now the total resistance over here will be 2R naught plus delta R3 plus delta R4, and from here it will be 2R naught delta R1 plus delta R2. So this is what over written is, or written over here. And then we, for the equivalent resistance, we take we need to add up the conductances. So we have to take reciprocal of these values and add them, and again take the reciprocal of that value to get the total resistance. So what we do is we use an approximation that delta R are too smaller than R naught, as these errors are too smaller than the actual value of the resistance. So what approximation we take is 1 upon 1 plus x is nothing but 1 minus x, when x is very small. So 1 upon 2 r naught. So the value when taken its reciprocal becomes 1 upon 2 r naught, 1 minus delta r1 plus delta r2 divided by 2 r naught. And similarly, for this, the conductance becomes 1 upon 2 r naught, 1 minus delta r3 delta r4 divided by 2 r naught. And when we add those, the total conductance will be the addition of those two. And again, we have to take the reciprocal, and using the approximation again, 1 upon 1 minus x is nothing but 1 plus x. So we have to take the reciprocal of this. So 1 upon this value minus x. So basically it comes out to be r naught in bracket 1 plus delta r1, delta r2, delta r3, and delta r4, addition of all those four deltas divided by 4 r naught. Now we have to find the standard deviation sigma of this value. And as all the four resistors are identical with sigma 1 as standard deviation, and which is of delta r by r naught initially, where we designed the resistor. So, and all are identical to that one. So we can say that this value is nothing but this can be written like this, which is 1 upon 4 in bracket delta r1 by r naught, delta r2 by r naught, delta r3 by r naught, and delta r4 by r naught, an addition of all of them. So, but these are again, they are randomly available for each and every individual resistor. So all we can do is we can take the root of square of all sigmas. So what we are doing is 1 by 4 root of sigma 1 square, sigma plus sigma 1 square, plus like 4 times we have taken the sigma 1, as they are identical to the initial resistor we assumed, and it was sigma 1. So now from this we get the standard deviation as sigma 1 by 2. So what is the outcome of this this analyzation we did as of now? So we have four resistors connected in this way, and it is nothing but those four resistors connected together in this way, in which we are increasing the width and length by the same factor. So if we increase the width and length by factor of 2, then our mean deviation reduces by the same factor. So basically the proportionate of mean deviation is inversely proportional to root of omega L, and this is what we said earlier over here. So we proved the concept for the resistors, and this law holds for all the other components present on the sheet. So from above discussion, we saw that the absolute values varies with wide variation, but we can rely on the ratio of the resistances to be accurate. But the accuracy has to be quantified given by the sigma, and sigma simply gives us the distribution of difference between two resistors divided by the nominal value, and sigma is basically the mean deviation. So now let's talk about the capacitor. So again, we have our P substrate, and on which we have different layers of metals, and the thickness and spacing between these metals is fixed by the process team, and we only have the freedom from the top view. So from the top view, this is something how we can realize a capacitor with the width and the length, and the capacitance between two sheets is given by C equals to epsilon r and epsilon naught. We know the value of epsilon naught, and typically for oxide we used in IC design, the epsilon r is equals to 4, and now we are remained with A by T. So area is of our capacitor, which is width into length divided by the thickness, and the thickness is also fixed by the process team. So these all values are fixed already, and which are known as capacitance per unit area times what we are left with is width by length. So we have the freedom uh, over here while designing a capacitor. So even the special metal plates are used to construct the capacitor. Still, it offers very less value. Why so? Because a typical capacitance per unit area offers a value of 1 fetafarad per 1 micro square. So 1 micron square. So this is very less capacitance offered by a typical capacitance per unit area. And so if we want 10, like let's say if we want a capacitance of 10 picofarad, so we need 10 picofarad divided by 1 petafarad per micrometer square, and this comes out to be 10,000 micrometer square. And thus, to make a capacitor of this area, let's take the length of 100 micrometer and width of 100 micrometer, which will give us the total area of 10,000 micrometer, which is basically giving us a capacitance of 10 picofarad. So this area is so large as compared to other components, so which can this area can probably hold an op-amp or even a complex digital circuits which can perform significant signal processing. So this is so large as compared to it, and to have a capacitance of nanofarad, it's quite impossible because the area because of the area constraint, and typically it is limited to few picofarad. So making a capacitor of high value is not preferred because it takes too much space. And just like resistors, there will be mismatch in capacitors as well, and the mismatch or the deviation is again given by the same law or the same formula. Larger the capacitor will make, more they will match to each other. But the how large it should be is limited to few picofarads. And if we have a circuit where matching of capacitor is important, then we will be forced to use the larger capacitors. So now it turns out that the matching between the capacitor is somewhat better than the matching of resistor. And now let's talk about the other reasons or other causes where due to which mismatches causes. So due to some system causes, there will be other mismatches which are other than the random mismatch we discussed right now, like we discussed just right now. So that was called as random mismatch. And apart from that, there are other mismatches as well, which are due to the systematic causes. So let's say we are making resistors which are identical, a pair of resistors which are identical. So for the best matching, we must have components aligned in the same direction and not in the different direction. And also some same environment conditions are also important. So while matching, so for best matching, we also need same environmental conditions. And if we have array of identical resistors, then the outermost two will be slightly different from all other which are in between. And the reason is that the capacitors capacitors are let's say resistors, whatever they are, whatever the component is, which are in between, has two neighbors. And thus they have nice matching, but the outermost has only one neighbor, causing it a little different from all other which are in between. To really match all of them, we introduce dummy resistors in the both ends of the array. So let's say we want to make four identical components. So we introduce two dummy resistors, and now we can say that all four are properly matched. So sometimes we also have to use multiple dummies for better matching, and this is how it's done. So same goes with capacitors. To be identical, they need some matched neighborhood. And now let's say we want R1 and R2, where R2 is twice the value of R1. So initially what comes to our mind is, let's increase the length of R1 and make it twice in order to get twice its resistance. And like it turns out that when we measure these two resistors after making the length twice, so actually the resistance of second one is not exactly equal to the twice of first resistor. So because the end parts, so near the ends the current is not uniformly distributed across the cross section. So as we know that resistance is given by sheet resistance times the area, and assuming uniform current density throughout the resistor, this resistance is calculated. But now when we double the length to get the double of the resistance, we come across fact that at the ends, the current is not uniformly distributed. So the reason that the current density is not uniform, we cannot realize R2 just by doubling the length. So doubling the length is not the solution, but the real solution is we have to make two identical R1s and connect them in series. So let's say if we have R1 and we want a resistor twice its value, so we will make two identical R1s and then connect them in series. And to make a proper matching, we will use dummy resistors as well. So this is how it's done. But again, if we have identical components in array, due to systematic gradient, let's say a system is designed and it's designed from this side to this side. So due to the systematic gradient, because of doping or the thickness, as we go from one side to another side, we have increased delta R. So let's say we have resistance R, we have R plus delta R plus 2 delta R plus 3 delta R, and so on until until the last one, which gives us R plus n delta R. And this error is ascending error is caused due to systematic gradient, and the reason might be due to doping or thickness, whatever. So let's say this is what happening with our array when we are trying to make register R2, which is twice of the value of R1. So if this is happening with our case, so this is our case, and let's take some values to analyze this. So let's say our R1 is 1000 ohms, and we want some resistance R2 whose value should be twice its value. So basically we want 2000. So now what will happen is these two are our dummy resistors, and we have R1 as 1000. So due to such kind of error, what will happen is, let's say if it's 1000, it will be 1010 ohms, it will be 1020 ohms, and when we connect them in series, then the sum of these two is basically comes out to be 2030, and which is not equal to 2000. So the solution to this is, again, we have dummy resistors outside, and let's say we have like we make series of an array of resistors. So what we'll do is we will consider this, the middle part, as R1, and the outer parts as connected in series, we will consider that as R2. And this gives us this is 1000 plus 1020, which gives us 2020, and which is nothing but twice of 1010. So thus we can now easily make a register which is twice the value of given register. So I think these are few ideas and a few discussions based on the CMOS implementation in CMOS process. And let's talk more in detail in next video. So I think that's for all for this video. Thank you so much.